Tonight we're going to look at beginner control loops. There's already one of these presentations from last year, I think we did in 2021, that has most of the same slides, but we're going to look a little bit more into the actual code, and we have an elevator simulator running in the software, so we can look at that and play with it a little bit more too. But we still want to go over and get a full idea of how the control loops work and what they do for the robot and why they're important. Okay, so the idea behind control loops is that we're going to actually be able to use feedback from the real world to figure out how we should send the energy to our motors, right? How we actually send the voltage and apply it to the motors so that we can get it to do exactly what we want and not just guess by giving it some percentage of motor power or battery power like we normally do with just what's called open loop, where we don't have any feedback. So what is feedback? Feedback is using sensors to get that actual information from the real world. With feedback, like I said, you're not just giving instructions, you're also checking what's actually happening and modifying the instructions based on what's actually happening in the real world. In FRC, you can do feedback in a variety of different ways. The two most common is having the sensor values come back to the RoboRio and doing some math and calculations on the RoboRio to figure out what the output should be for the motors, or having one of the smart motor controllers, which are basically the Spark Max or the Talon FX Falcon 500 are the two that most teams are using now that almost everybody's using mainly brushless motors for our robots. And so both of those systems work. It just kind of depends on how where the sensor feedback is actually going and where that information is and which computer is actually doing the calculations. So that kind of changes what this diagram looks like for each of those setups. Okay, so yeah, so this just defines open loop and closed loop. Again, open loop just means you are running the motor at some percentage of the battery or maybe some specified voltage. So a lot of times this will get used, sometimes it's called manual control. This will get used on things that we're not really worried about their exact velocity, like how fast they're spinning. We just need it to work, and that's fine. So like a lot of teams, their intake control is just run as open loop, and you're just setting it, run at full battery power, spin it as fast as you can, bring the game objects in, and that's fine. And a ton of time that is fine. So I think our intake in 2022 was running open loop. I don't think we were actually running it full. We were running at like 0.8 or 0.9. And that just ran and it was fine and it sucked in the balls. But that does limit it a little bit when, if for some reason it's slowing down, it's getting stuck on something, you may want it to actually be velocity controlled, where you want to have a closed loop system so that it can detect if it slows down and apply more power to it. That can be helpful where you want it to only spin a certain speed, but then once it grabs the ball, it'll give it a little bit more power to actually suck the ball in. But there's other times where a closed loop is like the only way to do it, or the only effective way to do it. Something like an elevator, where we want to make sure we're setting that elevator to a certain position, a certain height above the ground. If all we had was open loop, you'd basically have to sit there and like tap the joystick up and down to try to like move the motor up and down a little bit to try to find the exact spot you want. And that would just never be faster than having a button that you can press that tells it to go to the exact scoring height that you want it to. Similarly, you wouldn't want to like have to move the joystick for our ball launcher to get it to the speed you want it to go to. We want it to automatically be able to go to a specific speed, and every time we launch a ball from whatever that distance is, or every time we tell it to go to that speed, we want it to be repeatable over and over and over again. So we get a really consistent robot, and a very accurate robot to what we're actually telling it to do, and it's not just based on whatever the voltage of the battery is at that moment. The control loop is programmed. It's basically a math function that takes in, we'll look at it in just a second. I don't need to go into that on this slide, but basically it's a math function that's based on the feedback to control the system. Okay, so in open loop, you give it some set point. Most of the time for us, that's going to be -1 to 1. That's how we do things in open loop. We're basically saying -1 is full reverse, 100% of the battery. 1.0 is full forward, 100% of the battery. And that's all it does. In closed loop, we add back in that sensor For most of our systems, that's going to be an encoder. It's able to tell how much the motor has spun, like how far the motor has spun, or also how fast the motor has spun, since you can do that with time. If you know you've spun 2 ticks in some amount of milliseconds, you can figure out how fast you're actually moving. So in this case, in a closed loop system, we have our set point, which is basically how fast we want the motor to be spinning, or how far we want the system to go. Some distance, some number of revolutions, something like that. So for an elevator, it might be to move 48 inches off the ground. For a launcher wheel, it might be spin at 3,000 RPM. Just some actual unit that's based in the real world that we're able to measure and check if we've actually reached that set point or that target or that goal yet. The motor itself is still actually moving based on some percentage of battery, right? It's not like the actual electrons are still the same. We're just able to change those really quickly and differently based on that feedback. So instead of just giving it a constant voltage and just telling it to go to that, we're going to change that based on how far away we are from the target, how close we are to the target, all the different parameters that we're going to be able to change, and what we call tuning to actually control that motor better. And this is what allows us to be just way more efficient and way more effective at making robots do what we want them to do. Okay. The measurement is what the sensor is actually reading at that time. So that's what we're measuring back from the system. So for the elevator, that's its current height. So if our set point is 48 inches, but the elevator is actually at 10 inches, that's the measurement is 10 inches and our set point is 48. Launcher wheel, it might be off, so it might be at 0. And then the actual value that we mostly do our computations on is based on this thing called error. So error is just the difference in our set point and our measurement. So where do we want to be minus where are we? So if our elevator wants to be at 48 inches and we're only at 10 inches, our error is 38. Same with launcher. If we want to be at 3,000 RPM, but we're actually at 0, our error is 3,000. Error can be negative if we want it to go in reverse, or if we want to move down. Like if we're actually at 48 and we want to go to 10, our error would be negative. That lets us reverse the motor output or slow down or anything like that. Error is probably the most important thing because we're using that difference in set point and measurement in all of our math in multiple different ways in the math, but all of the math to be able to figure out how to get to whatever our target is. Okay, so here's a quick elevator example. So we can go through and we can figure out the error at each one of these positions if we want. We already did this one, so if our command is 48, if our set point is 48, we already know that this one's 38, 48 minus 10. For B, we're doing the same thing, 48 minus 30, so that's 18 inches. And then for C, it's 48 minus 46. Did we go through and do that? Yep. So that's 2 inches, and for D, it's 0 because we're at our height, right? So that's where we're measuring our height here. And so if we're at our set point, our error is 0. If we're at where we're commanding it to go, we don't have any error. That's all going to 0 out. And that should make our math easy for that one, hopefully. Okay. So the way control loops work is we have to think about how do we actually determine how much voltage or energy do we give the motor depending on how far away we are, depending on how big that error is. So you can imagine that in the A situation, we want to give the motor a pretty good amount of power because we're really far away from where we want to be, right? We're much further away in A than we are in C. So the basic idea is as we get closer to our set point, as that error gets smaller, we want to reduce the amount of power we're giving the motor so that it slows down and we don't just like go way past it. Like if we just always said, if we're not at our set point, give it 100% power, we're going to blow right past our set point. Then we're going to have to try to come back, and it's just going to move. It's going to bounce around all the time. It's not going to work very well. It's just not going to be a very well-tuned system, because it's not going to get us to exactly the point we want to go, and stop right there and be accurate and repeatable and reliable and all of those things. Yeah, so A should move faster than D. B and C, similarly, elevators should be moving faster at B because we're getting ready to stop than it is at A. And then the question is, how basically do we make that equation? So we know we have this error value. What's the simplest equation we need to be able to get this output? And it works out to, this is what we consider proportional control. So if you ever hear the term PID, which gets thrown around a lot, the P in that acronym, and we'll go through, and we'll touch on the others here in a second. Proportional is the most important part, by far all of it. As long as if you understand proportional, you can get an idea of how everything else works. And most systems, a ton of FRC systems can work just with a proportional control loop. And that's the main thing we're going to talk about tonight. Proportional just means it has a constant ratio to our error quantity. So we need the equation that just takes error, outputs a velocity that gets us a smaller error, and as the error gets smaller, ideally that output gets smaller and smaller as well. And so that formula is incredibly easy. It's just error times this constant. So we're going to call it Kp, and it's just a number. It's a number that we tune, and we can change, and we can figure out how to make our system work so that as error gets smaller, our system slows down and lets us hit the set point that we want to, or the target value that we want to. Kp is going to be different for every single system. If the systems are very, very similar, so like each one of our swerve modules, we end up just using the same Kp for each of them because they're all built basically the same. They're all using the same motors. They all roughly are the same. In theory, we could probably tune each of them slightly differently and make them slightly better because they're not all built fully identically, right? They have slightly different parts. There might be a little bit of, one might be mounted a little tighter than the other or something. But most of the time for that, we don't care as much. It's going to work the way we need it to. But we'll definitely have a different Kp for our swerve modules than we do for our elevator, than we do for a ball launcher or anything like that. Those are all going to be very different because they have different, the systems are all built differently. Let's see. Okay. So with some, this is again a very basic example, but this allows us to get an idea of how we can somewhat calculate a way for us to know what Kp should be, or an approximate value for it. So if we know that at 38, if our error is 38, we know we want the motor to be going at 100%, and we know at error 0, we want the motor to be going 0%. We can put those values in. So we know 38 times Kp is going to be 1, and 0 times Kp is going to be 0. This should be obvious. And then we can go through and we can just kind of make that, we can solve for Kp up here and say Kp equals 1 over 38. And that would mean basically as soon as this starts moving, it's going to start slowing down because it's going to have an error smaller than 38. So it's going to start slowing down, and it's going to get incredibly slow at C, right? Because we're going to be outputting 0.052, so around 5%, which may be, depending on the system, that might be too slow to even move it. Just depends on how it works there. So a lot of this, again, we have to go through and test and figure out if it works. But the concept or the idea is what we want. We want it to be going quickly at the beginning and then slowing down as we get to D. If we don't want to slow down that quickly, maybe we want to slow down a little bit later. So in this slide, it basically says maybe we don't want to slow down until we actually reach the B state, so when we're 18 inches away. So in that case, we would put 18 equals 1, and we would solve for that. So now 1 over 18 is Kp. And that does lead us to some weird example where at 38, it's going to try to tell our motor to go 211%. That's not something it can do. You can't give 200% of the battery. almost all of the code for a robot knows that. So if you try to output 200% to the battery, it caps it at 100%. It already does that for you. There are times where you may want to do it inside the controller, but most of the time all of that's going to be kind of done in the library. So it's okay if the error is really big and you multiply over KP and it ends up being some value way bigger than 1. That's fine because we have checks in place in the software that basically say if our output is greater than 100%, cap it at 100%. So that works there. So that means anywhere between this A and B state, the motor is going to be going 100%. And then once it gets to B and starts passing it, it's going to start slowing down between B and C. And it'll slow down even more between C and D. And we can get something out like that. Okay. So similarly with a launcher wheel, so if we have something where we want to actually set velocity now, like how fast the wheel is spinning, and not the position of the wheel, or not the position of the system like on the elevator, they're very similar concepts, but they're a little bit different, and we'll go quickly kind of to where the difference is here. So if our command is 3,000 RPM and each one of these is slightly different, we can see what our errors are at each of those positions, which is easy enough to see currently. We can look at what the KP is and figure out how to calculate that. The difference, though, here is that at D, once we're at 3,000 RPM and our motor's spinning at the speed we want it to spin at, we don't actually want to turn the motor off at that point, right? If it's spinning at 3,000 RPM and then we give the motor 0 volts and tell it to turn off, it's now going to slow down immediately because it has no voltage anymore, and that's how systems work, right? Once the motor's off, it's going to slow down. So that formula, that really basic formula of just error times KP, doesn't quite work here for what we want. Like, there's ways to sort of make it work and kind of fudge it to where it'll like turn on and off very quickly around that 3,000 value. But normally that's not going to be as precise as we want it to. And so since our output should never actually go all the way down to 0, we introduce a new term that we call feed forward. And feed forward lets us basically tell the system and like our control loop some information that we already know about the system. So we know that if we're telling it a set point of 3,000, the motor is going to need some amount of voltage to keep itself at 3,000 RPM once it's there. And that normally for something like a launcher wheel, it's going to somewhat scale with the RPM range that we want. So we introduce this new value, KF, that stands for feed forward, and it just multiplies not by anything to do with the error, so it's not really, it's not feedback. That's where the term comes from, right? It's not feedback, it's feed forward. So we're telling the system something that we know about it already, that it's going to need to know to be able to control the motor the way we want. And so we have this set point value, or target value, or goal value, depending on which library or controller or whatever you're using. And it's 3,000. So in here, it's always multiplying this value by our KF term. KF, again, is just like KP. It's some number that we're going to tune and make up or decide how to set that value, and we can go in and adjust it up and down to kind of change how the system speeds up or slows down as it gets to our system or to our set point. And so we're just helping predict how fast the motor should be spinning or how much voltage the motor should have when it actually gets to our set point. And so these systems work really well. This also works when if you really think about the elevator system, you probably don't want the elevator motor to completely turn off either for most elevators. Gravity's still trying to like pull it down most of the time, so you probably want some amount of voltage going to the motor to keep it up. So something like this can help there too. You may not want it to be set point times KF. You may just want it to be plus some constant voltage, like maybe it's the amount of gravity, the amount of voltage it needs to overcome gravity at all times, since it doesn't change with velocity as much here. So there's different ways to do feed forward. This is the way that works largely for velocity control. So anytime we're controlling a launcher or if we wanted to control the RPM of our intake, or we did it for our feeder wheel last year, so we were feeding the ball into the launcher really consistently. All of those use a setup pretty similar to this, where you have a KP value and a KF value, and you're changing those a little bit to make sure the motor's spinning at the right RPM that you want it to by the end. So in this case, if we wanted to say that our motor needed to spin at 0.5 to be able to actually maintain 3,000 RPM, we now have a little bit more complicated of an equation to solve, but it's not too bad since this is 0. Since the error here is 0, this makes it relatively easy to solve for KF. And we can do that here. And so we just get that KF is this tiny value, 0.5 over 3,000. We can plug that in everywhere else, and now we can solve wherever we want 1 to be. So if we want 1 to be up at A, or maybe like last time we wanted 1 to be at B, we could solve that equation wherever we want. I don't actually think we do it in the slides. But yeah, so you could easily solve for, so we solved it here. So yeah, so KP ends up being solved here if we wanted to basically immediately slow down as soon as it starts spinning up. You could solve for KP at 0.00016. You could solve it down here if you wanted it to be 1 at the B value. And you can just basically change how the whole system, how the motor responds to the different errors and how much voltage it gives it. And all of that's kind of just based on what we actually want to see happen in the real world. If we want it to slow down immediately, you could do this. If you want it to slow down a little bit later, you can up your value of KP to make it output more with a smaller error. Okay, so yeah, so this is most of the key vocabulary for what we went over. And now we're going to look at the actual simulation example for the elevator. And I did that in about the right time I wanted to. Okay, so back to our little elevator example, and we can see kind of what we're looking at. In the Romy code, we have an elevator simulator system. So this elevator sim folder. And it has a few different classes in it. Elevator, elevator commands, elevator config, and elevator simulator. We don't need to worry about the actual simulator. That's kind of just on the back end and going to show us how the examples work. But we will go through elevator commands and config here just in a second to show how it works. But first, let me go ahead and simulate the robot so we can pull up and see what we're talking about when we say simulate a robot, or simulate the elevator. Okay, I'm going to close some things that we don't need. Let's see, we shouldn't need that. And I'm going to make this a little bit bigger. Okay, and we don't need LEDs for right now. All right, so this display right here allows us to simulate an elevator. So it's blank right now. When we go into teleop mode, I can press Z on my keyboard, and that acts as the A button on a gamepad. And it's going to set it to a set point. And so it's going to have that elevator move up to some value. And we can see that it's actually simulating it all. So we have a encoder here. Encoders 8 and 9 are basically showing what the actual values could be. And over here we have a PWM output, which is just like a motor output. So this is giving us our -1 to 1 value for what we're outputting to the motor. So what percentage of the battery is going to the motor. And when I press Z, we can see it's giving it full power right now, which is probably not ideal. So we're basically stalling the motor into the top limit of the into the top of whatever the elevator can go. So like it's max height, and it's just running full out and just going all the way up. So we probably want to figure out how to make it not do that and have it actually go to whatever our set point is that we're trying to get it to go to. So let's figure out why that isn't working the way we want it to. Okay, so let's see. Let's start, I guess, back at our controls so we can see what we're actually telling it to do. So in Pilot Gamepad, this is where we set up the controls for the robot. And in here, we're telling it gamepad.a_button.while true commands go to height 30. So we're telling it to go to 30 inches. But it doesn't seem to be doing that. It seems to be going to some height larger than that. So let's figure out what's going on in there. So we can look through here, like when we're in the code, if we want to figure out what a method does, we can just right click on go to height and then go to definition. And this will show that command. So this is a command that's in elevator commands. It has go to height. It takes in a integer height. And it then makes a new run command. So this is a command that's going to run some method for as long as this command is running. And it's running the robot.elevator.goToTarget method. And then this robot.elevator bit right here is so that it requires the elevator, which means that no other command can use the elevator at the same time. So if we start some other command like the stop command that also requires elevator, this command will end and stop will take over, which is what we want it to do. If we run the stop command, you want to make sure that this is no longer running and still telling it to go to whatever the height is. So that's why it always has this second little thing to comma whatever the system is that's running on it that it requires. Okay, so similarly again, we can go to target inside of the elevator class. And we can see how that works. So in here, go to target is getting the PID output from mController. And mController is a new PID controller that we built for the elevator. So it's an instance of PID controller. So this is all built in to WPI-lib for us. So at some point, if we want, you can go in and actually see what this all looks like and how PID controller works. We don't need to for right now, but if at times if we're using it and something's not working, seeing what the source code looks like and being able to go look into it is definitely helpful. The things we need to know for sure, though, are what we're actually setting it to. So this PID controller is built with a KP, a KI, and a KD. For right now, since we haven't talked about what KI and KD are, we're ignoring those. So we're just using KP here, and then KI and KD are 0, so they're not affecting what we're doing. Our go to target PID output equals controller.calculate mencoder.getDistance. So we're getting the distance from the encoder that we built up here. And we have, and then we're going to actually set the voltage output with PID output. So what does this mean? So if we're using set voltage, the way we set it up with set voltage, that means we're, instead of sending it a -1 to 1, we're going to send it -12 to 12. Our battery's voltage is roughly 12 volts. And so we're going to tell it, if you want to go reverse, go -12 volts is full reverse, 12 volts is full forward. And so that way it's a little bit more consistent based on if the battery voltage is changing, ideally the motor is still being a little bit more consistent and using the true voltage and not just the percent of whatever the battery voltage is at. That's important to know what we're actually outputting though, because that means our controller should be calculating voltages, and actually we want to make sure this PID output is in that range, -12 to 12, and not -1 to 1. And so that's something we'll have to potentially keep in mind when we're going through and fixing and seeing what's not quite working in our elevator simulator at the moment. Okay, so the easiest thing for us to play with is to change the elevator KP. So if we go to definition, so that's going to be inside our elevator config class. So config is where we put all of our constants, anything that might just be anything that we're going to tune and configure for that specific robot. We keep in here. And so elevator KP is here. Right now it's set to 5. If we lower this a lot, we should see some change in the simulator when we run it again. Hopefully it doesn't just go all the way to the top, because it was working at some point. It doesn't completely right now, but I might have been messing with it. So we'll be able to solve that, and we can see if we can tune it and get it to actually go to the value we want it to. Okay, so if we do this again, so yeah, so it's still going all the way up. So it's basically going all the way to distance of 0.1. I think something else is changed on here. Hold on, let me see if I can't. Because it's only saying it's going to distance point. Yeah, so it's only getting to a distance of 1. So that doesn't work for where we expect it to be able to go all the way to like 38. So something else changed in our configuration that isn't working the way it used to. Let's see if we can't figure that out. Okay, so we're supposed to be giving it a min elevator height of 2 and a max elevator height of 50. But for some reason that doesn't seem to be working the way we want it to. Elevator. We might actually have to look in simulator for that. Mechanism. Huh. Okay. Let's see what we're doing here. Something's not quite right. Find all references. Okay, so yeah, so we're configuring our min and max elevator heights, so that should work. We're telling it to simulate gravity. That's all just other stuff about how it's working. Why did this stop working? Meters to inches. Elevator get position. Angle 90. That should work. Okay, something's going on with the mech 2D width. 20 height 50. That is weird. Okay, if we make KP 0, we can double check that it's working at all. So this should make it to where it doesn't do anything. So if it's still moving, we know we have a problem. Because it's definitely not supposed to move if KP is 0, because that would be multiplied by error, and the whole output should be 0. So that's at least a minimum what it should be doing. Okay, so that works. So when we hit Z now, we have the little yellow box. It's not moving at all, so that's a good sign. So let's see if we make it just a really small number. Does that change what it's doing? It may just be way out of tune. We can figure out what our scale is in a second if we need to just double check that the simulator's working at all the way we expect it to. All right. So now with that small of a number, it's still not moving at all. All right, so we're going to up it a little bit by like 10. So we know 1 was sending it all the way to the top, so let's see what 0.1 does. All right, so that worked, but it's still sending it all the way to the top. It's just sending it a little bit slower. So that's not quite working the way we want. Let's see, we can check in our network tables view. We can pull some of the elevator stuff and we can see exactly where we're at. So when we come up here right now, So yeah, so it's going all the way to 39.37 instead of going to our instead of going to 30 like we want. So maybe we can change, let's see, make sure that that's still true. Yeah, so it's supposed to go to 30, and it is not doing that. So let's double check if it's just a value problem or if it's somewhere else we're having an issue. All right, go into teleop mode, hit it again. Yep, and it still went all the way past where we wanted it to. It is not slowing down at all. So that means it's not getting our error calculation probably in any way that makes sense. So something else just isn't quite working. Because it should reverse once it gets above it. It should reverse everything. Our error should have to be negative. We're past where we want to be. But that's not happening right now. All right, let's see what we did wrong. Here.
Just started reversing.
I don't think it reversed. I'm willing to look again. I'm pretty sure that was just when I let go of the button. But we can see. Pretty sure it didn't, but who knows. All right, so if we hit it again. Yeah, so holding it, as long as you're holding the button, it won't reverse. Once we let go, it knows it can reverse. So once we let go of the button, it'll slow down because it drops the motor to 0 and it simulates gravity and everything, and everything comes back down. But while we're sending it to 30, it's still going forward the whole time. So that may be like a units problem somewhere. There's a lot of issues where that could happen. I don't know if this is just something where I had it fixed somewhere else and then didn't push the fix. That's probably what went on. Let's see where that it would be. Okay, so to target, calculate, get distance, height. It is, okay, so my guess is here. Somewhere we're sending stuff in meters, but we should be in inches. So let's see if that works. So if we do units dot inches to meters here. I think we did that already, didn't we? Didn't we do that in... No, we didn't. So go to target, just sends height. Okay, so let's try that here. Let's try to send our units in meters and see if that solves it. So all of our M controller settings, don't seem like we do a bunch more to the controller other than calculate, but our encoder, get distance, yeah, so that's just there, and our encoder set distance per pulse is in config. Let's see what this is, distance per pulse. No, so this is in inches, so this is 2 times, yeah, so that's 2, which is, oh no, it's elevator drum radius. So yeah, so drum radius is in meters, because this is inches to meters as well. So that means this elevator encoder distance per pulse is in meters, but we were sending it our height in inches. So instead of thinking we were sending it 30 inches, the whole system was sending it 30 meters, and that's why it just kept going higher, which makes sense. Because it was trying to go way higher than our elevator could ever actually go. So we're going to simulate that and see if that solved our problem. All right, so for teleop, we now are getting very little output. That's probably because our KP is now way too small. since our error changed a lot. So we're going to change our KP again, put it back to where it was. It was back at 5 when we started. We'll see if that makes more sense. All right, let's try that again. There we go. All right, so now it went up and it got to 23 inches. Even though we told it to go to 30, it only got to 23 is what it looks like. But that's definitely closer, and it's like stabilizing there. And you can see that it's outputting some really small value right now. So that's not quite what we want it to do. So we can see what happens if we give it a much bigger number. So this is what we talk about when we're talking about tuning. We're changing this value to try to get it to hit our target correctly. So in this case, we're going to try to get it to 30. We'll see if we can actually do that. So we're just going to double it, see if that's better or way too much. This is one of the good things about the simulator is we're not actually crashing anything, any part of the elevator into anything if we mess up here. All right, so it bounced up. It got up to 26, and it seems like it went a little bit over that and then came back down. So yeah, so it didn't quite hit 30, but it got close, then it came back down, and now it's staying at about 26. And there's only so much we can do with KP. We may not get it to be exactly 30 ever when we have only a KP or only a P controller. Since we have gravity, like fighting in things, and we don't have any of that feed forward term at the moment, there may not be anything we can do. So we can try to make this big again, and we'll see it like, ideally this should have it go way past 30 and then come back down if everything is working correctly. And so this also happens in our robots when we're doing tuning and PID control. We'll have it what's called oscillate, where it's going to go past the set point and go back above it. So hopefully that's what happens here, or something like that. Yeah, we can see it got a little bit closer, but it like bounced over it and then came back down and then got close to the value, but not quite there. So you can see it goes quite a bit over 30 and then comes back down. So we wouldn't want this to be how the actual robot worked. We'd want it to get to the point and never pass it. We want it to very nicely hit the point that we're telling it to go to and just stop there. That doesn't quite work with just a P controller. So we can add things to it if we want. So we could add some form of a KF to it. So KF would be something that's just going to fight gravity. So if we wanted to very easily put in a simulated KF, there's better ways to do full feed forward. There's like motor feed forward built into part of WPI Lab and stuff. But in this case, we're just going to tell it some value that is going to just be constantly added to the motor while the elevator is running. So during our output here, we're going to tell it to just add to our output the value of KF. So it was able to suggest that for us already. That was GitHub Copilot doing that. And so we can check what that does. And that might have it, that 0.1 might be way too much. It might just cause the elevator to move. We don't really know. But this is a lot of what we can do is we can just sit there and play with those values, play with the tuning, see how we can get a system to behave the way we want. Again, right now this is still a relatively basic system. We can go into a little bit more. So yeah, so 0.1 wasn't quite enough. It doesn't quite get up all the way to 30. So we may need to add more to the KF or change the KP some. A lot of times if you change one, you may need to change the other. So it may be something like we're already adding 0.4 but lowering this or something. You normally don't want to change too many at the same time because you don't know which one exactly is actually affecting your output. But a lot of our setting changes for the actual robot is adjusting values like this and trying to get the output that we want. that we actually want to see in the real system. So that got us closer. So now we're a little bit closer to 30, and we definitely shot way over, but we came back down. So we can see if we can get a little bit closer again. All right, so now we're at 29.5. So we're already a bit closer. All right, let's go all the way to like 0.8. All right, so that's like 29.9. So that's probably good enough, but now we're definitely jumping over it a little too much, so we can lower the KP now that we have our KF set a lot higher. So let's see if we can't lower our KP a little bit and see if we can get the jump past the set point to be a little bit less. Yeah, so that was a little bit less. We probably were a little not as close to the value as we were before, so we're 29.8. But we definitely don't go way past it like we were doing before. We're up at like 32 and came back down. So we may need to adjust the KP some more, adjust the KF a little bit more, and we can see what our output actually ends up being, getting us a little bit closer to where we want to be. Oh yeah, so this is, again, this is in voltage, so this is less than 1 volt. So if we drop this a little bit more, maybe change this to 1, we can see if we can get a little bit closer to 30. There are a bunch of other slightly more advanced steps you can take as we're trying to make the system a little bit better. So we already talked about the idea that PID exists. So we have those 2 other letters in there, the I and the D, which we'll go over at some point when we need them. We don't really use I very much in FRC. D we do a little bit, but D just kind of lets us slow down as we're approaching the target, so we can kind of smoothly stop right at the target we want to be at. Yeah, so that was a little bit better, but now we're all the way up at 31, so it was a much smoother ascent. It didn't really go over it, but now we're past it. So we probably want to lower our KF a little bit so that we're not shooting past it anymore at all. We should be able to get pretty close to 30 now. And then the other part of this, you also have to think about, for a system like this where we're moving an elevator up and down, we might have multiple set points that we want to go to, like there might be multiple scoring heights. There we go. So that got us to 30.4, so that might be enough for what we need. But as we start making this actual competition robot, we would definitely tune it even more to hit exactly 30 inches, or maybe 30 inches is what we think we want, but then when we go on the actual playing field, it's actually 30.5 inches, so this might be even better, and we'll have to tune it a little bit to change that. There's a lot of tweaking we have to do for any sort of system like this to get it to where we want it to. This also might be too slow, like maybe we want it to get there faster than this or slower than this. So playing with all of those different numbers and tuning values is how we're able to actually accomplish all of those things.